Hey guys, here's your second installment in Chapter 7. The first video I made was only over Section 7.1. There was a lot in there with Max Planck and his theories, and now on to Section 2 and 3, still studying quantum theory and the electronic structure of atoms. So let's get to it. Our next mystery here is the photoelectric effect, and the photoelectric effect was something that was observed, and this little GIF here, you're seeing what the effect was. And the effect was the fact that you could shine light onto a metal, and if that metal had been charged, electrostatically charged, it would become discharged if you shined on that metal surface a certain frequency, and that frequency was called the threshold, well, termed the threshold frequency. So your textbook has a picture here that I've covered up a little bit with my GIF, but the idea is that there is light coming in, and as it comes in, it shines on the metal surface, and your book uses HV to indicate light, and that when that happens, an electron is given off, and then when that electron is given off, you see an electric current go through, and that's what this PhET simulation is showing you. So if you have time to go look at the PhET simulation of the photoelectric effect, and experiment with that a little bit, it helps you to understand what was being observed. So when the photoelectric effect was being explained by Einstein, what he said is that light has both wave nature and particle nature. And that's why waves can, light, which is waves, can cause this effect. This effect where light waves hit the metal and eject electrons was actually caused by more of a particle nature. And that's because this little slider up here in this animation or this simulation that you can play with showed that until you reach that threshold frequency, you would not see any electrons being ejected. And since that was the case, it was what Einstein was saying is, according to what Planck's idea was here, remember E equals NHV, that's like particle nature. And that particle nature is what explains the fact that a particle could kick out a particle, and that's what was happening. So he termed these things a photon, and a photon is a particle of light, and we call it HV. If I put HV above an arrow in a chemical equation or reaction, that means that it is facilitated by light. So the mathematical relationship then that was determined is that this photon of light, HV, and W is called this work function, and kinetic energy is the kinetic energy of the ejected electron. So this work function is a different value for every element, and it depends upon the element itself. But a work function is the amount of energy that is required to overcome the fact that the electron is being held by the atom. So this energy, HV, comes in, hits the surface, overcomes the work function, and the kinetic energy and the electron is ejected. Now, if the HV, or amount of energy required, is exactly equal to the work function, then that electron will not have any kinetic energy. But if you look at this simulation up here, there's a battery attached to it. If there's a battery attached to it, you can turn that battery on. And when you turn it on, you can cause a potential difference across here. And as you do that, even if these things are directly equal to each other, I think you can make the electrons move by the fact that you have now a positive, negative side to this apparatus. So if it's not exactly equal to it, then as you put in more energy, you can cause those electrons to move faster. And during class week, I can bring up this PhET simulation and we can look at that. So again, we're still in the photoelectric effect and how that equation, this mathematical equation, was rearranged to describe what was going on. So originally here was our energy of a photon, and here was the work function, and then the kinetic energy was of the electron itself. So rearranging this, you can solve for the kinetic energy of an electron. And again, if these are equal to each other, then that kinetic energy would be 0. But if you exceed the amount of energy by exceeding that threshold frequency, this is a threshold frequency, you will impart kinetic energy to your electron. So in the take-home message from this idea was that light moves like a wave, but it transfers energy like a particle. So it's coming like a wave, but then when it has that certain amount of energy that is wavelength dependent, it hits a particle and it can knock it out almost like a ball hits another ball. So here's another little GIF. I went GIF happy with this, just trying to give you something to look at and us to talk about when I'm doing these recordings, is that here is the photoelectric apparatus again. Now the original photoelectric apparatus wasn't like this, and I'll post a video for you that was just showing, it was called an electroscope, and an electroscope was not like this. It didn't have batteries and all this other stuff, but you could charge it with static electricity. And then when you charged it with static electricity, you would shine light onto it. Say this was my electroscope. The electroscope was kind of neat. It had a box, and then it was attached to a little piece of gold leaf down here. And that gold leaf would be hanging down straight if it was not charged. But if you rubbed the surface of this metal up here with something and imparted some electrostatic charge to it, you would charge it with electrons. And then when you turned on the light, this thing would move. And that would mean that it was being discharged and the electrons were leaving the apparatus. So there wasn't a battery like you're seeing here. But either way, the photoelectric effect is described by this mathematical equation, which is a takeoff of Planck's ideas. So let's use this a little bit here in a problem. The work function of titanium is a certain energetic value. If we want to know the kinetic energy of an ejected electron, if a certain frequency is shined on it, we can use that same relationship like we saw. So the kinetic energy of the electron is equal to your HV, which is going to be from your threshold frequency, minus the work function. So if we put those numbers in, there's your H, there is your threshold frequency. Or actually, there is just light. It doesn't say that it's threshold frequency. But if we do these two calculate, let me calculate just in case, the 6.63 exponent negative 34 times 2.5 exponent 15, I get a value of 1.6 times 10 to the negative 18 joules. See, because your seconds cancel, I'm in joules. This number is larger than the work function. So that means the electrons that are ejected are now going to have some leftover energy. So I'm going to subtract 6.93 times 10 to the minus 19th, and I get this 9.65 times 10 to the negative 19. And that's of one ejected electron. I always thought this was confusing because I thought, well, what if I eject a mole? If you eject a mole of them, you would have to multiply that by Avogadro's number. And it's a very large number then. It is 580 kilojoules. I would need 580 kilojoules to eject 1 mole of electrons in that apparatus. So anyway, that's how the work function is used in the photoelectric effect to determine speed of ejected electrons. So on your fun sheet, I call this one a think sheet because it requires a lot of thinking. That in this one, the idea again is to look at the threshold frequency and the work function, and I have gold here and I have potassium, and determine the speed of an electron. So your goal here is to calculate the kinetic energy of an ejected electron for both of these metals. And then you could determine the speed, because if you remember, kinetic energy is equal to 1/2 mv squared. So if you know the kinetic energy of the ejected electron, you could calculate the speed given the mass of an electron. Now, of course, you'd have to look up the mass to put into there. So you have everything you need for this one, right? You have kinetic energy is equal to HV minus W. So that's how you would determine the kinetic energy of the ejected electron. Now this problem, I was reworking my slides here and I found this problem here. I really like it because it's not necessarily the photoelectric effect. Maybe it is. See if you see what I have some pictures in here that show what's happening. Apparently, I went to hyperphysics. And if you go to hyperphysics, it's really, really good for understanding almost all of these things that we're dealing with right now. And I went to there and it was talking about that X-rays that are produced, that are used to X-ray people, I guess, or your teeth or whatever, are produced by bombarding copper with high energy electrons, and then X-rays are emitted. And apparently when you bombard a copper metal with electrons, that with high energy electrons are moved around within that metal. And since they're moved around within that metal, other electrons fall to fill those empty spots. And then those energy given off during that electron transition is X-rays. So as far as what we're going to do here, we want to calculate the energy in joules associated with a photon of the X-ray if the wavelength of that X-ray is 0.154 nanometers. Now remember, if you have a wavelength and those H and C are constants, you can calculate energy. And that's really all this problem does. I mean, it's showing you that if you have a wavelength or a frequency and you also always have H and C, you can calculate the energy of a photon. And that's what we did here. And in this hyperphysics, this is where I found this picture. Just moments ago, I was reading this problem. I thought, I'd like to have a GIF. Well, they didn't have a GIF, but they did have this picture. And this was pretty interesting, is that those high energy electrons bombard a copper surface. And in so doing, they knock electrons around in this copper metal. And when those electrons fall back down, they eject, X-rays are emitted. And those can be used to do an X-ray on somebody's mouth, or like if you're at the dentist or something like that. So when you did this math here with hc over lambda, this is the energy of one photon of the X-ray. So one photon. And that's why it's such a small number. So that would be joules per photon. So you could determine how much energy you are being hit with if you knew how many photons of X-ray radiation you were X-rayed with. So let's go on to mystery number 3. So we're still talking about quantum theory. The photoelectric effect helped us understand that electrons travel that light travels like particles. So light was acting like a particle, and that's why it could eject a particle. Planck's theories, where we had E was equal to NhV, he was saying that light was like a particle because these are the number of particles of this H, which is the particleness. Remember, that's H. That's Planck's constant. And then this was the frequency of that light. So again, E equals NhV was saying light was behaving like a particle. So now looking at mystery number 3, emission spectra of atoms, this is another experimental observation that was made, that if you passed light through a prism, you would get a separation of lines, and then those lines were completely dependent upon what was being energized over here. So if this one is hydrogen, there's hydrogen gas in here, and then electricity is hooked up to a high voltage, and we'll play with these this semester. That light is given off of a certain color, and then when you pass it through a prism, you get these 4 main lines. Now, you might see some hydrogen spectra that has more lines, but these are the main lines. And those, when I say main, they're the brightest, they're the most common, that type of thing. So yes, this is hydrogen. So, and these wavelengths have a certain, these lines have a certain wavelength with them. And you'll notice they're around, this one's I think around 407 or something like that, I forget. And then, so those are kind of like a fingerprint of that element. So I found a GIF that I thought was pretty cool, that you could visualize why this was occurring. This is going to illustrate the Bohr theory of the atom. And the Bohr theory of the atom, energy hits an atom of an element, and that electrons are promoted to another higher energy level. And as they fall down, they give off energy, and that energy, if it's in the visible region, we can see it. So if you follow this animation, it looks like that, how do they go up? See, as they go up, like this fell from 6 down to 4, and that's a line, and then fell 4 down to 2, and that was a line. 6 down to 4, that's a green line, and 4 down to 2 is a purple line. And it's also showing this 2, one of the 2p electrons, going from 2 up to 4 and falling down, and that's red. And this 4 down to 2 is also red as purple. I thought there was one. So we have a red line, we have a green line, and we have a purple line. Now this, I was noticing, I found this GIF, and I was noticing this line spectra does not look exactly like the one in your book. So I think this one has more lines than the one in your book. The one in your book shows only the yellow line. So Bohr looked at all these experimental observations and said, well, I think this is what an atom is. Then I think this is where the electrons are and what they're doing. And he proposed that they were in certain orbits like this, and that they would have, and when energy was absorbed, those electrons would be promoted, and as they fell back down, that photon of energy would be ejected or given off, and then that would create one of the lines in the line spectrum. So his model suggested that electrons can only have specific energy values. That means the electrons can only be in certain spots, and that certain spot in the atom had an energy associated with it. And then light is emitted as that electron moves from one energy level to a lower one. So when I say emitted, that means given off. You'll notice the direction of this arrow. But if I reverse this direction and it hits the electron, you would see that electron being promoted to a higher energy level. So that's an absorption of energy to promote the electron. Now the energy value here that in Bohr's theory has to do with where it is. This n value is either n equal 1, n equal 2, n equal 3, or whatever. And this RH is called the Rydberg constant, which is a constant that has to do with optics. And it was created and discovered through the study of light. And so this Bohr was already working with that in his toolbox, and he said, oh, I think these are related. And so this principal quantum number is illustrating where those electrons are in the atom. So the energy of that electron has to do with this Rydberg constant and where the electron is. There it is, the Rydberg constant. And notice it's in joules, and it's a really small number. So according to this idea, that electrons that are in n equal 1 will have a certain value, and then if they're in n equal 2, they will have a different value. So when they transfer in between these, you will get what's called a delta E. And that change in energy is going to be indicative of the photon of light that is given off as that relaxation occurs of the electron. So Bohr was thinking of, kind of stair-steppy in the way that here's an electron, it's higher, it falls down. Now notice it only fell down one spot. And notice if this is the nucleus down here, and this is the center of the atom, these energy levels start with n equal 1, n equal 2, n equal 3, 4, 5, 6. And you'll notice that those energy spaces are getting closer and closer. They're much further apart down here. So if something falls from n equal 2 down to n equal 1, that's a much larger energy drop, and your energy will be a larger value. And when that does this drop, what this figure is trying to illustrate is that it's a green ball, because this is going from 3 to 1, and that's what is gives off a green color. And this is going from 1, 2, 3, 4, 5 to 4. And that is a lower energy value, and that's a red line. And remember our Roy G. Biv spectra, as far as a rainbow is concerned, that violet has a higher energy and red has a lower energy. So this red line only fell 1, and they were very close to each other, and therefore it was a lower energy value than the green. Roy G. Biv, I forgot my G. So the green, this is higher energy over here as far as those colors and wavelengths, and then this is lower. So the reason that 5 to 4 is only for one thing, it's only a fall of 1 energy level, and those energy levels, as you get higher up like that, are further away or closer to each other. So the fall is not as large. And that's what that's illustrating here. This is green light of a photon and red light of a photon. So once this was discovered, line spectra was being researched and experimented on, and different series were discovered. And those series, they're called that because you'll notice in the Balmer series, they all end on n equal 2. Now, I think that's going to show up here for a minute, so I don't want to get this too busy, but the energy of that photon, when it changes spots, there's that delta E I was just talking about, is the difference of final state minus the initial state. So if the final is lower than the initial, you'll get a negative value. If the initial is lower than the final, you get a positive value. So there's the initial and final. Those are the energy values that from the Bohr theory of the atom on the previous slide. So now the difference of those is the delta E. So where it starts and where it ends dictates how much energy is either given off or absorbed. So looking at this picture over here, we're going to see that there's different values for these n values. If there's an initial from 2 to 1 or 3 to 1, or 3 to 2, that's the red line, those are different series. So as far as the Balmer series, in the Balmer series, they all end on n equal 2. But that electron that was there can be higher. It can be all the way up to 7 and drop to 2. And you'll notice when it's up at 7 and drops to 2, it's black. And that's black because it's of a higher energy than the violet, and it's not visible to us. So these are the visible lines here. And the Passion series all end on 3. The Bracket series all end on 4. So as an example, this is like one of your fun sheet questions. Calculate the wavelength of a photon emitted by a hydrogen atom when its electron drops from 3 to 1. So we just utilize this formula here and see 3 to 1. It's the final would be 3. 1 would be, no, I'm sorry, 3 would be the initial. 1 would be the final. And you put those numbers in there. So 3 squared is 9, 1 squared is 1, and then you get a change in energy of this value. Now it's negative, and it's negative because it fell, and since it fell, it has lower energy. Now I want to know the wavelength. So remember that wavelength is equal to hc over lambda from Bohr's theory, Planck's theory. And then if we just go ahead and put energy of our photon in there, we can get a wavelength. Now it looks like, I don't know if you guys can see that wavelength because I got my picture up here. There we go. So now you can see, there you go, you can see all those things. So now the lambda, which is the wavelength, notice it came out in meters, and I can leave it that way, or I can convert it to nanometers. And then I said, where is this? Where is this on the electromagnetic spectrum? Now, I always remember that Roy G. Biv is from 400 nanometers to 700 nanometers. So according to this is blue indigo. Actually, this is violet. And then this one is red. So this number is higher. It's up here. So it's in the infrared region. And that's what this was showing here, in the infrared region. So we could look here. Now, on that previous slide, it was 822 nanometers, or 8.22 times 10 to the minus 7th meters. So if we look on here, let's find meters here, times 10 to the 7th meters. Oh, that's not meters, it's in nanometers. So we would still want to look at 822 nanometers, and that would be in here somewhere. It's really hard to see. I don't really love this because you're saying, where is 822 nanometers? I mean, as far as 10 to the third is 1,000, right? So it's going to be a little bit lower than that. But we saw that, I don't think it's visible. It's going to be right around here somewhere. Maybe right there. Okay, it's in the infrared region. That's what I was trying to look at there. Now on your fun sheet, here's another fun sheet question, and I've asked you to consider a hypothetical atom and this is a problem from directly out of your textbook. I thought was a good one for understanding the Bohr theory of the atom. And the Bohr theory said that there were levels, and those levels had energy values associated with them. And the question in this one is, what is the wavelength of the photon needed to excite an electron from 1 to 4? So you could get a change in energy value there, and once you get a change in energy, you can use, again, E equals hc over lambda, and you can solve for wavelength. Same thing for letter B. What is the energy in joules a photon must have in order to excite an electron from 2 to 3? Same idea. And then when an electron drops from 3 down to 1, that's emission. What is the wavelength of the photon emitted in this process? And then now finally explain the Bohr theory of the atom and how it explains the line spectra. So go back through and read that and try to put that in a nutshell. So that's it for this recording for sections 2 and 3 for chapter 7. So work on those fun sheet questions and we'll go over those some more later.